Well, let's see how you did. I hope you didn't choose C. There is simply no such thing as an absolutely precise measurement. It's impossible. It's also not A. This has nothing to do with being careful. We assume that we are always careful when we make measurements. If you made a measurement and realize that you weren't careful, don't write it down, just redo the measurement. It's also not B. The uncertainty or the precision in the measurements has nothing to do with mistakes. We're going to assume that all our measurements are correct. That's another reason we make multiple measurements. It helps us catch our mistakes. If one of your measurements is very different from all the rest, chances are you made a mistake and you should discard that measurement. So it's D. There are going to be other things, in this case your reflexes, which will result in a larger uncertainty than is possible with the stopwatch. Your reflexes probably introduce an uncertainty in this measurement of several tenths of a second, in fact. Quite often we have some set of measurements, and we need to use them to do some sort of calculation to obtain a calculated result. An issue that arises is that those measurements have limited precision. That means any number we calculate from them will also have limited precision, and we need to know how to determine what the precision of that calculated result is. Let me illustrate this with an example. Suppose we want to know the center-to-center distance of two cylinders. This is the sort of thing we would often need in various experiments, or an engineer might need to know this characterizing the behavior of some machine. So hopefully from the diagram it's clear that that capital R is this. Now, that's actually a little more complicated than I really need for this example. Let's just focus on adding D and R1. Let's suppose we've measured them, and we measured D with a ruler because perhaps it was a little too long to do with our calipers, but we know R1 to higher precision because we were able to use calipers to get R1. So if you just plug that into your calculator, this is what we get, but this ignores the precision of the numbers. If you were going to do this calculation the way you learned probably in elementary school, you would write 2 zeros after the 2, and you'd carry out the calculation and get the answer that your calculator gives you. But remember, the reason we've cut off 31.2 after the 2 is not that it's zeros after that, it's that we don't know what those digits are. So think about what that means. Question mark plus 6, or I don't know plus 6, is certainly I don't know. And I don't know plus 7 is certainly I don't know. And so we really don't know either of these digits, which means they're not significant figures. And so we would round off. Because it's 0.67 and that's bigger than 0.65, we would round up. This illustrates the rule and the reason for the rule for sig figs of added or subtracted numbers, which is that we round to the number of digits past the decimal of the number with fewer digits past the decimal. So as another example, look at this addition, and you should work through and verify that you understand how I got what I got here. Multiplication and division is slightly simpler. Here we round to the number of significant figures, not digits past the decimal, the number of significant figures of the number that has fewer significant figures. So if I use those same numbers, 1.247 and 0.0039, and I multiply them, I get an answer that has two significant figures. I want you to notice, in one case, adding the two numbers, I got 4 significant figures. Multiplying the same two numbers, I got 2 significant figures. You should work through the rules and verify that you see why. An important thing to remember about this is that it only applies to measurements. So for example, if we calculate a radius from a diameter, the radius is just the diameter divided by 2. You might think then that the radius should have 1 significant figure, because surely that 2 has 1 significant figure. But that's not correct. That 2 is not a measurement. It's a precise number. By definition, the radius is exactly half of the diameter. And so that 2 has an infinite number of significant figures, which means the radius would end up having the same number of significant figures as the diameter. I want to finish by talking about order of magnitude calculations. There's a supplementary video where I talk about how to do them and give an example. Right now, I just want to talk about why we do order of magnitude calculations. For many students, that's not obvious other than because your professor asked you to. Suppose you're designing a wastewater treatment plant that uses algae. One thing you would need to know is the gas exchange rate of the algae. That's going to be difficult to determine whether you calculate or measure it. Probably you're going to measure it, but how? How you go about measuring it would depend on how big you expect it to be. And so, in a sense, you have to know how big it is before you can find how big it is. You do a quick order of magnitude calculation to get a rough idea how big it is, so that you can make a decision about how to measure it. Another reason we often do order of magnitude calculations is to check the answers to more complicated calculations. Suppose you wanted to calculate the speed of a rocket 2 minutes after launch. That's going to be a complicated calculation. It's going to involve a bunch of calculus. You might actually be better off writing a computer program to simulate it. And let's suppose you come up with 2,100 meters per second. No, that's 2.1 kilometers per second. Well, is this answer reasonable? Because there are lots of errors you could have made in the very complicated calculation that could give you an extremely wrong answer. And by extremely wrong, I mean not even the right order of magnitude. And so it would be useful to do a simple order of magnitude calculation that at least gives you an idea, roughly, of how big the answer ought to be.